understanding weather. If I don't get to the questions you have about weather, please ask them and we will go where you need to go. But what I want to focus on here is I want to make sure that you understand the data standard for hourly weather streams. There is an option to bring in daily, but I'll be honest, with numerical weather modeling, the way it's going, you don't have to worry about daily. We should be aspiring to hourly, so that's what I'm going to focus on today. I also want you to know how to choose between one of two hourly fine field moisture code methods, which one to pick for your fire simulation. So those are your learning outcomes. It all starts with specifying a weather station location. And we're going to go through these steps in a moment, but essentially, there are two schools of thought when creating a simulation. Some of you might be going away and creating a case study, and in doing that, you will probably be looking for a nearby weather station, a physical sensor that's out there collecting data. Generally, we're looking for something that's within 30 to 40 kilometers, maybe closer if you're in steep terrain, for it to be representative. The other thing, if you're in steep terrain, is maybe thinking about the elevation of the station and the elevation of the fire. That might be more important than the distance. Either way, that's one concept we can use to think about a weather station. But if we're in predictive mode, and that's what I'm going to focus on more, is that predictive mode, we don't have to tie ourselves to a physical sensor because we're using forecasts. The weather station can be the fire location itself, and you can get the nearest weather forecast for that fire location, and that can be your station. So I just wanted to name those two kind of concepts. Even though we call this a weather station, it's literally just, it's locating your weather data within the landscape you're modeling. It's putting it on the grid. And we don't necessarily have to tie a weather forecast to a station 40 kilometers away. We can bring in a weather forecast right over top of the fire. When you create a weather station, it will automatically look to see if it overlaps with your grid extent. And if it does, it will auto-populate the elevation, provided you've given it that data. You don't have to accept that. Sometimes the elevation will be slightly off because of the resolution of your elevation data, or it might be integer values and you've got a precise elevation and you might see that it's like 1 or 2 meters off. Don't worry about it. Really, in the great scheme of things, you could accept what's there or plug in the precise value, but just know that it's doing that. And if you see that elevation auto-populate, that's why it's doing that. And the final thing I want to say about weather stations is you don't have to restrict yourself to just one. I think this is more the world of automation, but you can bring in multiple weather station locations, or we could think about them as numerical weather forecast locations, and cover our entire landscape with different forecast points and have spatial weather model options turned on so that we're interpolating weather between those points on the landscape. And imagine a really large fire, a 300,000 hectare fire. You may have different weather on the north end of the fire than you do on the south end. And so that's, again, where having multiple weather stations can be advantageous. You want to be using the weather in the locality of where the fire is spreading. And if it's spreading on both the north and the south ends, you may want to have separate weather streams reflecting on that. So that's what you can do with weather stations. We're going to demo that in a bit. Let's look at the data standard. Weather is brought in as a text or CSV file. CSV stands for comma separated value, but you can open them in Excel and edit them in a spreadsheet setting, which makes it quite handy. Looking down the table here, these are all of the header names that must be present. You must have the hourly header, which describes the date, and it's in day, month, year format. You must have an hour header, which describes the hour of the day as an integer from 0 to 23. There is no hour 24. Hour 24 is hour 0. You must have a temperature column, which reports temperature in degrees Celsius, RH as a percentage, or relative humidity as a percentage, precipitation in millimeters, wind speed in kilometers per hour, and wind direction in cardinal degrees. Again, the header names are as indicated in the table. If you use other headers, it won't recognize the data and you will get an error message. If you have FWI system values, you can include them in your weather stream, but they're not, you can also just provide a starting code and then Prometheus will calculate your fire weather indices through each hour and each day that you've provided. So they're optional. You do not have to have FFMC, DMC, and DC in your weather stream, but if you do provide them, that is what will be used in your simulation. That can be a handy feature for kind of case study work where you might want to force it to use something on certain hours of the day as opposed to calculating using the equations we're going to look at in a moment here. Okay, we talked about time zone earlier. Time zone is important because we're dealing with a lot of temporal data, time sensitive data. And so when we bring in weather, it represents an hour of the day. And if you pick the wrong time zone, you could be out by an hour or more. And so when the FWI system is calculating daily values, it's looking for noon weather. And if your noon weather is off by 1 or 2 hours, you're not actually going to be using noon weather, and that will throw off your FWI calculations. So when I said earlier, pay attention to the time zone, particularly if you're on a border of a jurisdiction, that is why, because you will likely be bringing in your weather data in the time zone you're operating in. And if you inadvertently skipped over the time zone that automatically populated in your landscape properties, you might be out by a couple hours, throwing off your calculations. So pay attention to that when you create your project, and also pay attention to the time zone you're retrieving your weather forecast in. Make sure they're the same. Okay, 2 methods for fine fuel moisture code calculation. There's a diurnal option, the Lawson option, and there's an hourly option called, it was published by Van Wagner in, I think, 1977. In the dialogue on this slide, this is from Prometheus, you can choose one or the other. And so we're going to talk about how do you choose which one to use, because it's going to make a difference. So this graphic is out of the weather guide for the Canadian Forest Fire Danger Rating System by Lawson and Armitage, published in 2008. I have uploaded that document to the Canvas in the module we're in. If you want to reference, I think it's appendix, I want to say 3, where they describe this in really gory detail. A good read. Anyways, Lawson is the dotted line, Van Wagner is the solid line, and I'd like you to pick up on a couple things. We're showing kind of 2 days of data here. The Van Wagner is not showing much recovery in terms of the hourly fine fuel moisture code through the late evening hours and early morning hours. It's pretty flat compared to Lawson, whereas we get much greater recovery through those late evening, early morning hours with Lawson. You can see that by the amplitude of the curves going up and down as we go from midnight to noon to midnight to noon. And that's all well and good. So let's look what happens when we put rain in. Let's put some rain in just after noon and see how these curves respond. And you'll see that the Van Wagner curve, the solid line, responds immediately. It drops right down as soon as that rainfall registers in the hourly data, whereas the Lawson does not respond until the next afternoon. You'll see that the dotted line, which is the diurnal Lawson method, drops at noon the next day. Okay, and there's a reason for that. The Lawson is essentially a set of lookup tables, and it's not responding to hourly weather data. It's assuming a typical diurnal trend or pattern in weather, and it resets what that pattern in hourly fine field moisture code is going to look like each day at noon. And so it won't pick up any kind of big change in weather, particularly precipitation, until the next day. So that's a real key thing to be aware of. But there's some other things. And so we're going to kind of compare and contrast the two. Again, this is really well documented in detail in the weather guide, which is up on the Canvas board there. But let's look at Lawson. So it's an empirical approach. It is based on actual fine field moisture samples taken from a lodgepole pine site near Prince George, BC. Kind of represents mid-latitudes. Its advantage is that it does give reasonable results in the absence of precipitation. And when you have this kind of diurnal trend that we would call typical, where you've got overnight recovery of temperature and relative humidity. And so in doing that, you get this recovery of your fine field moisture code, right? They drop off. The FFMC drops off in the late evening, early morning hours, which will then correspond with less fire behavior, less spread potential through those hours when using Lawson. On the disadvantage side, it does not respond to hourly changes in temperature, RH, wind speed, or precipitation. Again, it assumes a diurnal pattern and it picks up new information the next day at noon. There's a slight little nuance with RH. It is looking for kind of which table to look at in the morning based on your morning RH, but really it's just determining a lookup table. It's not really responding to hour by hour by hour RH. Finally, and a disadvantage of the Lawson is because it's empirical, it may not be a best representation of FFMC and other litter types outside of lodgepole pine forests or other latitudes. So when to use it? Recommended when you have no precipitation in your forecast or your observed data. Recommended when you have good overnight recovery, temperature and relative humidity, and that kind of typical diurnal trend. And finally, recommended for mid-latitudes, again, where you've got that typical diurnal trend. May not be so good when you go north and you've got longer daylight hours, and that diurnal trend may not be as typical. So let's compare that to Van Wagner. So Van Wagner is a mathematical approach. It's not based on actual field measurements. And so the advantages, though, because it's a mathematical approach as opposed to lookup tables, it does respond to hourly changes. Remember that graph. As soon as the precipitation occurred, it dropped right off. So it's very responsive. Its disadvantage, as we saw, is it will stay elevated during the evening and early morning hours. It doesn't have as much recovery. And so when to use this method, generally, if you've got precipitation observed or expected, this can be a good one to use. If you have poor overnight recovery, where you don't want that amplitude in the FFMC through the evening and morning hours, this can be a good option. It will allow you to grow fire through the evening better than the Lawson method will. And again, we mentioned previously, this one is probably better for northern latitudes when you've got long day length, and you may not have that overnight recovery. That is as much as I wanted to say about weather. Now, let me stop sharing this. We are going to go to 11 o'clock, and I think what I want to do, I'm going to demo how to import weather, but I think it's going to be better to do that after lunch because we can do it all in one fell swoop when we're going to be importing some other things like ignitions, and it'll keep it tighter. I think I want to do our next breakout while we're on the topic of these two different methods. And so again, I'll encourage you to look across to your Canvas board in the fire modeling folder location, and we're going to be looking for breakout question 2. I'm going to bring it up on screen. I'll introduce the discussion topic, and then we'll set you off, and we're going to repeat what we did earlier this morning. We're going to do 5 minutes of individual reflection and then 10 minutes of group discussion, and that should get us to the lunch break time. So let me bring it up on screen. Give me a moment. Once you've downloaded it, it should look like this. Your question is, for each of the 2 hourly weather streams, would you, and so there's 2 weather streams in the Canvas board, and the file names are provided here. One of them is weather_B3_hourly ... The other one is weather_TPA_hourly ... blah, 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 blah. They're both CSV files. You can open these in Excel and look at them in a spreadsheet. For the B3 station, I've given you the latitude, 51.6 degrees, and it's a lodgepole pine, Engelmann spruce, subalpine fir kind of mix of forest types. For the TPA, it's at 56.4 degrees of northern latitude, and the predominant forest types are black spruce and some mixed aspen and white spruce forests. And so again, your question is, for each of those 2 weather streams, would you use the diurnal Lawson method or the hourly Van Wagner method to calculate your hourly fine fuel moisture code? And I'm looking for you to explain the answer with your group. And so we're going to do this one the same way. I'll give you 5 minutes to kind of download those files, look at them in Excel, think about the question. If you can't remember those criteria I shared with you, they are in that weather guide, which is up on the Canvas board as well. It's Lawson and Armitage 2008. Spend 5 minutes thinking about this. Dan will then put you into your breakout rooms for 10 minutes. And when we come back from the lunch break, we'll kind of go around to 2 more groups and talk about their responses, okay? So I'll put up a timer for 5 minutes. Go ahead, go find these files. At the end of the 5 minutes, we'll put you